Well, I just sort of introducing you to one of my recent works, developments and testing of foraging strategy for low-cost swarm robots. Um, what we had initially was, after we have worked briefly with swarm intelligence, we thought of testing it on robotics, as robotics being my area of interest. So how about like we deploy those algorithms on robots and see the behavior, so that we get to know something new in real time. So for that purpose, many people are working in that area. Okay, there are a few rules actually swarm robots should have, which was defined by Errol Sahin. Those three rules are: they should be robust, flexible, and scalable. Robust in the sense, if you kill one ant, do you think the whole colony is going to die? No, they are robust. Next thing is flexible. They should be able to do different jobs. A single ant which acts like a hunter can also act as a guardian for the whole ant hill. And scalable. Whatever 10 ants can do, 100 ants should be able to do. The similar criteria are applicable for the swarm robots, and these are the three things which Errol Sahin has recommended while following the application of swarm intelligence in robotics. Well, actually, these are the existing swarm robots, SBots by Marco Dorigo. EPUC is an educational swarm robotic project where students can work and deploy their own algorithms on that. iSwarm is actually funded by the European Union in the development of this small swarm robots. The initial version of this iSwarm is actually Jasmine platform. And quadcopters, as I told you, SLAM is one area of application. Where you can map the area where or surveillance an area where each of the quadcopter can share an information with the other quadcopter. This is being developed by in the GRASP laboratory by Vijay Kumar, and actually we also had a similar idea. We thought of developing our own platform for a cheaper cost or lower cost, so that we can actually these robots need to be multiplied. If even a single robot costs $1,000, if I go for making 30 robots, it costs around 30,000 rupees. So if I try to reduce the unit cost of a robot, that will help me in developing or deploying my algorithms, whatever I have thought of. So our primary target was to minimize the cost per unit robot. So and then what exactly we want to do, or what exactly we want to test on these swarm robots was the first question. So for that we made a strategy. We just we just questioned ourselves what kind of a target we can achieve. So the first the first question was the simplest of all is to do a random search and then locate a particular target. That means I'll leave the robots in a room. They should be able to search for a target and let me know where exactly is the target with reference to the initial point or the nest, whatever you have seen in ants colony optimization. Okay, so before deploying that algorithm onto the robots, we just wanted to check the feasibility of the algorithm by simulating in 2D and 3D environments. Okay, well, after that the next step was to check it on real robots. So first, what kind of assumptions we made? I just wanted to give a brief introduction to this so that you will understand what exactly happens in a swarm also. This is a very simple robot, in fact. These are nothing but these black rectangles. Whatever you see are nothing but your infrared sensors, whatever are present in your remote control. These things can communicate with an AC or a TV, right? They blink at a particular frequency. So these are nothing but your infrared sensors, and there are also detectors beneath that, photo detectors. So whenever this pulses a signal, this would be received by another robot. So we made an assumption that it can only communicate in 8 directions, because it has got a line of sight and a span or the region within which it can receive a signal or transmit a signal. So these things actually overlap, these regions actually overlap. So this was the initial assumption we made. So based on that assumption, we wanted to simulate our algorithm of foraging. Before I introduce you to that algorithm, I just want to tell you how we simulated. This is nothing but your two-dimensional your matrix. Okay, we have used simple commands to generate this. These are nothing but your swarm robots. Do you see that? And this is your target, this one. The yellow region you see here is nothing but the range within which a robot can detect the target. Because the target also should be differentiable from the other robots. So it has got a particular frequency of communication. So it would be blinking its own infrared signals at a particular frequency, different from the robots which you see in this arena. Okay, so this is your two-dimensional mat or the top view of an arena. Okay, or your configuration space, what we call. So the search space is 100 cross 100. The target coordinates are 50 cross 50, and target range within which a robot can detect is 50, and the number of robots we have deployed is 25. Okay. Well, that was in 2D, and 3D it was like this. You can see the sensors on the top. Okay, on the in the 8 directions. This we developed in virtual reality, linking up with MATLAB, and the target is similar to the robot except for that it doesn't have any actuation mechanism. It cannot move, it can only stay there. But whereas a robot can move anywhere, or it can take a decision based on the kind of signal it receives. Well, what exactly was our strategy? You would be surprised, it is a very simple strategy, but yet the outcome of it is very complex. It is very similar to how we behave towards achieving a particular target while going in groups. You might be playing treasure hunt, right? Or say for example, you have gone to a new place and you are searching for a food stall. What will you do when you are going in a group? You would first, the best strategy is to first disperse. Say for example, you have got a walkie-talkie. You are talking to each other. Now what would you do? The one who finds the target first would communicate with others saying that I found the target. Okay. Or otherwise when you don't have a walkie-talkie, you will start shouting, saying that I found the target. Now this fellow, this robot, this is the target, okay? And this is the robot, okay? As soon as he falls into the target region, he'll start shouting, I found the target. So that is called message protocol 1. So he'll start blinking light at a particular frequency. Okay, so that is message protocol 1. So what it should do? What is the reception? Reception is target. I'm getting a target signal. So what should I tell? I found the target. Now the second fellow falls into the region of this first fellow's communication region. Okay, he's actually not falling into this region. He's falling into this region. Okay, so what will he do? What kind of a message is he receiving? He's receiving a message from his friend saying that he found target found. Now what he has to communicate? Penultimate target found, or something like my friend found the target. Okay. Now what is happening? There's a chain building up here. Okay. So this seems to be very simple, but yet the outcome is very complex depending upon the range of communication and the type of communication also. Okay. Now there is this third category guy who has never found a target. So what will he tell? He cannot say anything. Nothing to say. He's here, he is not within the communication range. Okay. So this is the algorithm actually behind that. I would like to show the results straight away. Well, this is something very important when you are simulating. Whatever you have decided needs to be simulated actually to know what exactly the robots or the swarm behaves like. So for that purpose, we made some initial assumptions. As I told you in the beginning, that a robot can communicate in 8 different directions. So assuming that the whole mat or the arena or the configuration space you see here as a matrix, wherever the robot is placed, it would be assigned a particular value in that matrix. Okay. Whenever it is standing there, there are 2 overlapping matrices here. One is a location matrix and the other one is a message matrix. So for this location of robot, we'll check what is the value there in that message matrix. If my message matrix says target found, this robot will start generating a new message in the message matrix. It is something like, if you assume this as a matrix, you will see this yellow region is nothing but target found region. Okay, that means I'm assigning a particular value to that particular coordinate in the matrix. Okay, element in the matrix. Say for example, this value is rated high, 5000 number. Okay, so similarly, actually there is another color in this. Why don't you adjust that? There is a blue color also in this. Can you see the blue color also actually? It's not coming up properly in the projector. There's a blue color also around this. Blue is not cyan. Can you see that? This blue cyan actually, cyan color is nothing but your message priority 2. Okay, this is nothing but your message priority 1. So when we started simulating with these 3 basic rules, this is how the swarm was behaving. Initially this was iteration 1. with those simple rules. You can see the guys who have gone inside the target region are actually emitting the yellow message. Okay, let's call it yellow message for simplicity. And whoever is falling into the yellow region are actually emitting a cyan image. Okay, so after the whole iterations were carried out, for after around 1000 iterations, you can see that the swarm was able to identify the target. They have actually converged here to this target area. So I would like to show a simulation. I have just taken out the matrix part of it, message matrix part of it. Okay.
What is the target defined as circle?
Just as a circle, a region. Sir.
Circle?
Yes, sir.
Why are you getting space? Second and third.
This one, sir. This region. Yeah, this was actually defined as a square because I have made an assumption that it can communicate in 8 directions. After we started simulating it, it looks like this. Can you see this guys? Actually nobody is helping them out, and suddenly some fellow starts helping. They're stuck here and this guy starts helping them. These guys, nobody has helped them actually, so they are lost forever. Even if you do infinite number of iterations, they will never come to the target. As long as someone is there to help them, they will be left out. Well, how it looks like in 3D, actually there was this number of robots constraint for us.
How many iterations?
Sir, it went around 1200 iterations. This is in 3D. Actually, we had a constraint of increasing the number of robots. We made many different assumptions while translating this 2D simulation to a 3D simulation. Because whenever a robot starts getting a signal, there you might have not noted, there is no necessity of actually orienting towards the signal. But here, once the robot starts getting a signal, it should also orient while also moving along that signal path. So we just limited it to 10 robots. And there is a mix of pattern formation algorithm also, which is advancement on that. Actually, the range is not this. We defined something else. Graphically, we couldn't define, so we just made it up to here. So this is how it looks. And so our target was actually to develop something which is cheap for experimentation, a swarm robot which is very cheap to experiment with. As we were not exposed to many of the techniques available then when doing our bachelor's, I just did it with whatever was available in the market, right from the scratch. So we first designed whatever you saw initially communicating along the 8 directions. We just did it with this infrared transmitter. Actually, these are detectors. You can see the comparators here, and this potentiometer can actually define the range within which it can communicate. And this is a test module which we developed. Before deploying it onto your robot, we just thought of receiving signals and what kind of message am I receiving is what is displayed here on the screen. And after we stack it, here you have the microcontroller circuitry and here you have receivers, and you should notice that transmitters are kept ahead of the receivers because its own